In this video, we will discuss resonance structures. We will review how to draw resonance structures with correct arrows. We will discuss localized versus delocalized electrons. And we will also discuss what makes one resonance structure a little bit more stable than another resonance structure. So when you draw a resonance structure, you need to first make sure you identify every single delocalized electrons. These are delocalized electrons because that nitrogen atom does not have a double bond attached to it right now. And so what we'll do is I prefer to go clockwise. Delocalized electrons, if we have no charge, we need to find a pair of delocalized electrons that can generate a charge. And so we'll create a double bond. We will kick out the next adjacent double bond, and we will put those electrons on that carbon. And notice that when we create this resonance structure, even though we do have charge, they add up to be neutral, which our initial compound was neutral. And so that's how this needs to go. We will do this again. Again, we can do this again. It's not a perfect rule, but oftentimes when you have a 5-membered ring, you might expect 5 resonance structures. And if you had a 6-membered ring, maybe you would expect 6 resonance structures. Again, not a perfect rule at all, but just more of a tendency. And we get back to our initial structure. So what makes things most stable? Well, in this example, I would say that this first structure is most stable. Why? Because this structure is neutral. Completely neutral. You could also say it minimizes charge. Okay. Let's look at number 2. We're going to do the same sort of thing, except here we have a charge, and so that should be our focus. When we have a positive charge, we want to think about a positive charge being the absence of electrons, and so double bonds will move towards positive charges. And I can keep going, moving a second double bond. I know that I'm done because there's no more double bonds that I can move. Now, with positive charges, if you look at the back of your yellow periodic table, we have, let me draw a better picture. Okay, so let's say we have carbon number 1, carbon number 2, and carbon number 3. This carbon is primary because this carbon is connected to one other carbon, okay? This second carbon is secondary because it is connected to 2 carbons, one there and there. And then this third carbon would be called tertiary because it's connected to 3 other carbons. And for positive charges are most stable when they're on highly substituted carbons. Okay, so this one in the middle, this would be most stable because carbocations are most stable on highly substituted carbons. Okay, and this first one, this is a secondary carbon, this is a tertiary carbon, and this one is a secondary carbon. Okay, so now in number 3, I see charge, so my focus is going to be on charge, and this time it's a negative charge. And like we said in class, negative charges will behave as bullies, and they will kick out double bonds and put those electrons on the adjacent atom. Okay, so same thing will happen here. Now, from the notes, there's a couple ways you could justify this. I think I'd rank these ones a couple ways. Negative charges go best on highly electronegative atoms. So, there's good justification, and if you remember from Unit 1, oxygen's the second most electronegative atom. This is most stable. But what if we were comparing this second one and this third one? This one that I'm circling, the last one, this would be second most stable because carboanions, okay, notice that when we look at the one above, we said carbocations. Cations would be positive charge. Anions, that would be negative charge. Second most stable because carboanions are most stable on less substituted carbons. Okay. Now, in number 4, I don't see a charge, so I'm going to try to find a pair of delocalized electrons, and then I can generate a charge. Okay, they're on nitrogen, so I will create a double bond, and I will knock out those electrons and put them on the adjacent carbon. Nitrogen loses electrons when it creates a bond, and so it'll become positive. This carbon will become negative, and actually, that's all the resonance structures there are here. If you think about it, if I try to create another double bond, there's not another one to knock out. This one down here is too far away, and so I'm actually done. When I circle which one's most stable, I would circle this first one, and that was because it minimizes charges. Because it's neutral. Okay, now number 5, similar example, except this nitrogen has a negative charge. So we will create a double bond, knock out our adjacent double bond, and put those electrons on to the top carbon. In this case, those electrons are close enough to knock out a double bond. And so we get something like that. There is no more double bonds over here, so I know that I'm done. Finding the most stable resonance structure. As I'm looking around, they minimize charge, all of the same. They all have the same amount of bonds, so that's something that we'll see later on. More bonds is more stable. I would argue that this one is first for the exact same reason that we see up here. I'm just going to copy and paste it. This is most stable because the negative charge is on the most electronegative atom. This guy over here would be second. It's a carboanion, so I can go up here and say the similar type of thing. Carboanions are more stable on less substituted carbons. Okay, so notice that there's just a few things you got to memorize, and then you can, in your mind at least, copy and paste them. Okay, number 6. We have a negative charge. That's where I'm going to focus. Okay, so if I was writing a good reasoning, more than just a word or phrase, here is what I probably would say. And I'm going to label this structure 1, structure 2, structure 3. Let's see if Siri can get this right so I don't have to write it. Okay. Selection negative in and this should say equivalent. But on your test, you're not going to need to write huge long paragraphs like so. But you go to college chemistry, and absolutely you would have to. Okay, number 7. Now this one does not have any charge, so I'm thinking about my lone pairs, and what I see is I see a carbonyl group, and my gut is to focus on that one first. So we will create some charge here. This gives oxygen a negative charge. This carbon a positive charge. There's a pair of delocalized electrons. Many of you will probably do that step in one step. And here's what's kind of hard for people to understand, and I get it, is we get used to not drawing all the lone pairs of electrons, and that's fine. We would draw them if we needed them. For example, here we're showing the movement of electrons. We better draw those. But take this picture, and I'm going to copy it. And I would agree with you if you said that this looked okay for a second. But that would give oxygen 1, 2, 3, 4 bonds, which oxygen can have 4 bonds, but it would give it with one lone pair, and that's just not going to happen. So this one's actually done. You could make an argument, too, that we start with our initial picture here, and let me erase that. You could do this as well, have a new starting point. And so that's also acceptable. A good rule of thumb, and actually the only molecule that I know of where carbon has 2 double bonds attached to it, would be something like CO2. Not a bad piece of information to just sort of know. Okay, number 8. I'm going to go through these last ones a little bit more quickly. we see a positive charge, electrons will move towards a positive charge. I can already tell you that this second resonance structure is probably going to be the most stable. We don't have any heteroatoms, and we're already on a tertiary carbon versus a primary. And with carbocations, positive charges, those are more stable when they are on tertiary carbons. And so what's kind of nice is that if I labeled this A, B, and C, B is more stable than C, which is more stable than A. Resonance shows us how charge can be delocalized around a molecule, or how charge can be moved around a molecule. And so neither A nor B nor C exist in entirety. The real molecular picture is actually sort of a blend of them. But if I think about what is it more likely to be, B is going to maybe make up 70% of that picture, where C will make up 20% of that picture, and then A might only make up 10% of that picture. Okay, and number 8, this is probably the second or third time that we've seen this one, but it's a good one. Again, we expect 5 resonance structures. It's not perfect. You know, if I didn't get 5, I'm not going to freak out, but I'm going to anticipate 5, and I can already tell you the first resonance structure is going to be the most stable, because that is the one that is neutral. Okay, and your background in chemistry should lead you to think neutral compounds are much more stable than compounds that contain charges. So we go back to our original. We can say our original because neutral. Okay. This next one, I'm expecting that negative charge to go completely around this ring. It's not a very good one. I would say they all create the same amount of bonds, but structure 1 and structure 5, they may appear to be the same, but if you look closely, have you noticed that our double bonds have all rotated? And I would say they're most stable because they have the same number of bonds, but these two structures put the negative charge on the most electronegative element, oxygen. Okay, our last one. This one's a little bit weird. This is where we see a negative charge. I can tell you that first structure is going to be the most stable. Why? Because it's a negative charge, and negative charges are most stable on lower substituted carbons. And actually, as I think forward to this, our last resonance structure will also be the most stable because of that. Okay, so those two resonance structures are the most stable because they put the negative charge on the least substituted carbon